Hello everyone, welcome to debjitdecodes. So in today's video, we are going to solve the 0-1 knapsack problem, right? In the last video, we have talked about the dynamic programming. And as I have said that in the coming videos, I will be solving so many problems using the dynamic programming concept. So today we are going to see this 0-1 knapsack. Before this, in this playlist, there is a video available called fractional knapsack. And actually what was a knapsack concept and all these things, that is rigorously discussed in that video. So I would recommend, if you do not have any idea about the fractional knapsack or say knapsack in general, you can check that video first. So now I will be talking a little bit here as well regarding that. So now let us see what is 0-1 knapsack. So what is the definition of it? The definition is similar to the fractional knapsack. There is just a little bit change. What is the definition? What was the definition? Suppose say there is a bag and there are few items. Suppose here the item 1, item 2 and item 3. Item 1 will be giving you some profit, 60, item 2 is giving you some profit and item 3 is giving you some profit. And there are some weights for item 1, item 2 and item 3. There can be n number of items, right? So in that case, there is a max capacity of the bag, max capacity. That is, you can only put say 3 kg or 4 kg or 5 kg, anything. There is a max capacity of this bag. So you need to make sure that you will be putting item 1 or item 2 or item 3 because you cannot put all the items because there is a max capacity in the bag, right? So you need to put the items in a way so that your profit gets maximized. That's the thing we are doing in case of fractional knapsack as well. What we are trying to do, keeping in mind what is the maximum capacity of the bag, we were putting items in such a way so that our profits were getting maximized. That's the thing we were doing rigorously in case of the fractional knapsack problem. Now, what we were doing there? We were doing there like this. If say we have put 1, 2, 3, 4 items back to back inside the bag, and if we are unable to hold, or if I am unable to take the whole, say the upcoming item, that is the item 5, then you are taking some fraction out of it. Suppose say we have taken the item 2 completely, we have taken the item 3 completely, then we want to take the item 1, but there is, say the weight of the item 1 is suppose 10 kg, but there is only 5 kg left, 5 kg left. Then in that case, we can take the half of the item 1. That's why we are doing in the fractional knapsack, right? And that's why it is called fractional. But here if you see, it is 0-1, though the problem name is knapsack problem only. There the name was knapsack, here the name was knapsack as well. But in that case, it was fractional knapsack because we were able to take the fraction of one element or say multiple elements, or actually it will be one element only. You can check it out that why it will be one element. We can take the fraction out of one element. Now here we cannot. That is the exact difference between this one and that one. So what is the meaning of 0-1 knapsack? Because if you see, only this part is changing. There it was fractional and here it is 0-1. So what is the meaning of 0-1? 0-1 simply means either 0 or 1. That is either take or do not take. 1 means take and 0 means do not take. That is either you take the full element or you take you do not take anything. That is the thing. That is the thing it is trying to say. For an example, say you want to buy a particular toy and you want to put in a bag. So you cannot cut it, right? It will be wasted. So that's why you cannot always take the fraction out of it. That's why the fractional knapsack sometimes fails. So that's why we need the concept of 0-1 knapsack here. Either you take the whole, that is either you take the 1 or you take the 0. There is no concept of 0.2, 0.5, 0.7, nothing. So that is the definition of 0-1 knapsack. Knapsack simply means a bag. Inside that bag, you need to put either the whole element or none of it at all. You cannot take any fraction, right? Now, this is a very important question that as I have started this video saying that we will be seeing some dynamic programming approach, and this is one such example. So we need to first take care of the thing what fractional knapsack we are trying to do. What fractional knapsack we are doing? It was solving using the greedy approach. So we need to see whether this greedy approach will work here in case of 0-1 knapsack. Now if you see, there are 3 items, item 1, item 2 and item 3. And the profits and weights for each item is given. Now what we were doing in case of say greedy approach or in case of fractional knapsack, we were calculating the P by W ratio. As I am again and again saying, if you haven't checked out the fractional knapsack video, you can check it out. All these items are discussed very much in detail. So what we are doing? We are doing the P by W ratio, profit by weight ratio. So what is the ratio for the first element? 60. What is the ratio for the next element? 50. What is the ratio for the other element? 40. If you can see, 60 by 1, 100 by 2 and 120 by 3. Now according to the ratio, we are putting inside the bag, right? So what is the first element that will be picked? This one, item 1. So item 1 is inside the bag. Suppose there is a bag and item 1 is inside. Item 1 is inside, right? When item 1 is inside, because the maximum capacity is given is 5, so item 1's weight is 1, so the remaining capacity is 4, right? And total profit is, because the profit of the first is 60, so the total profit is 60. Now what is the second element that should go? This is this one, that is item 2, because if you see, this is the next value, item 2. So what is item 2? If item 2 goes there, what is the weight? That is 2 will be deducted, because the weight of the item 2 is 2, so the remaining weight becomes 2. Remaining weight becomes 2. And what is the profit? Say plus 50 plus, sorry, my bad, the profit was initially 60, and what is the profit now? That is 100. That is 100. So it is nothing but 160. Because if you put these two elements, item 1 and item 2, what is the total profit? 60 plus 100, that is 160, right? Now if you want to put the third element, this one, as you can check, the remaining capacity is 2, but the weight of the third item is 3. That means even though there is an item available, you cannot put inside the bag, because you need to take the whole of it. You cannot take the fractional, because if it was fractional knapsack, you could have taken the 2/3 of the item and you could have satisfied the condition. But here you need to either pick it or leave it. But can you pick it? Because the remaining capacity is 2 and the weight of the item is 3. So you cannot pick it, right? So this item 3 will not go inside. So what is the total profit you are getting here? 160. But if you can check by the naked eye, you can see, if you can take this item and this item, item 2 and 3, instead of this one, item 2 and 3, 2 plus 3 if you have taken, then what is the maximum profit? What is the weight first of all? The weight is 3 plus 2, 5, and the max capacity is 5. So this is getting satisfied, no problem, we can feed 2 and 3 both. And what is the profit we are getting in that case? 100 plus 120, that is 220. So if you can check, if we are following the greedy approach, this is via greedy approach. If we are following the greedy approach, then the profit we are getting is 160. But if you can check by normal naked eye, you can simply see that the profit should have been 220. This should have been the optimized solution. This should have been the optimized solution, but we are getting very less, right? Now if it was fractional knapsack, then what you would have done? You would have taken 2/3 of this 120, so it is 2/3 of 170, that is 40, that is 14 into 80, so it would have been added up, so it would have been 160 plus 80, 240, right? So it was the most optimized solution if you would have taken the fractional knapsack. But as it is 0-1 knapsack, you cannot take 2/3 of this element. You cannot take 2/3 of this element. So that case, when it is 0-1 knapsack, the profit is coming to be 220. But if you solve this 0-1 knapsack using the greedy, the profit is coming to be 160 only, right? So that simply means that greedy is not giving the optimized result when the problem is 0-1, that is either take full or do not take at all. It gives in case of fractional, but here it will not work, right? It will simply not work. So what we will do, what is the thing we can do here? If you can check, we can do the brute force manner first. Like we can go by this brute force manner first. At least we can try, right? Suppose there are 3 elements. Say item 1, item 2 and item 3. There are 3 elements. So if you want to see, if you want to check how it is working, so either you can take all the items, that is you do not take any of the items. Suppose the weight of all the items, say the max capacity is 5, but the weight of the first item is 10, second item is 20 and third item is 30. In that case, none of them will be picked, right? So all will be 0, because 0 is indicating here the item is not picked at all. Now in another case, there might be a scenario that is 001, that is only this item is picked, not this two. Then 010, then like 011, then 100, then 101, then 110, then 111. So if you can check, these are all the possibilities. That is, the last one is saying all the items are picked. This first one is saying none of them are picked, right? And in between, some of them are picked, some of them are not picked, right? So what are the, how many combinations are there for 3 items? 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 possible combinations for 3 items. Is there any pattern? If it was 4, in that case, how many possible combinations? 0, 0, 0, 0, then 0, 0, 0, 1. So you can find a pattern. What is the pattern? It is nothing but 2 to the power n. If there are n items, there are 2 to the power n combinations, or 2 to the power n kind of, these kind of things are possible. Okay, so in that case, if we use the brute force manner, because brute force will surely give you the correct answer. Why? Because it is exploring all the possible things. If you can check this one, if item 1 and item 2 are picked in case of 0, 1 knapsack, then what is the answer here? This is the answer here. The first 2 will be 1. This is the answer here. This is 1. The item 1 is picked, item 2 is picked, and item 3 is not picked. This will surely give you, if you explore all the possible solutions, this will surely give you the optimal solution. So that's why 1, 1, 0. This one is the optimal solution in this example. Right? But to find out the optimal solution in brute force way, it is taking 2 to the power n. That is order of 2 to the power n. That is huge, right? That is not polynomial, right? So that will take a huge lot of time and all these things. So that's why we cannot use this way as well. So who will be the savior in this case? The dynamic programming concept will be the savior in this case, right? So we will be seeing now that how we can solve all this, or what we can do in case of, say, any problem given, and we can solve it using the 0, 1 knapsack can be solved using the dynamic programming concept, right? So what we will do, I will just tell you. First of all, we will be taking this example. First, we will solve this example. I will show you how to solve this, how to construct a table, and how to get the optimized result or optimized output. Then we will be kind of seeing the recursive equation, and then I will be explaining you what this equation means, as well as I will be showing you the tree and tell you that how the properties, that is, what are the properties that should have, that is to have apply the dynamic programming. I have talked about in the last video. The first thing is there should be an optimal substructure and overlapping subproblems. So how these concepts are coming here, I will be telling. But first, I will be solving this one. Then I am coming to this one. Now see, there are 4 items given. Item 1, item 2, item 3, and item 4. Right? And for each item, there are some profit. For each item, there are some weights. And the maximum capacity is given as 8. And we need to solve using the 0, 1 knapsack. That is, you either take full or you do not take at all. Now see what we have done. We have constructed a table. What is the size of the table? The row is indicating how many items are there. That is, if you can check, there are 4 items, item 1, item 2, item 3, and item 4. So 1, 2, 3, 4, one extra row is added, that is for 0, when there is no item at all to indicate that thing. So if there are n items, there should be n plus 1 rows. And now if you can check, for the column part, what it is indicating? The column is indicating that what is the max capacity. What is the max weight? What is the max weight given in this equation or in this question? 8. So it should be 1, 2, 3, 4, 5, 6, 7, 8, and there is one extra column, just like the rows we had, that is indicating the 0. So initially, when there is 0, say this particular thing, how to solve, I am coming step by step. So initially, when there is 0, there is no items, so there shouldn't be any profit concept or anything at all, right? First of all, before going ahead, let me tell you what will be inside these cells. What the things are, first of all, said that the row is indicating the item number. How many items are there? This is item 1, this is for item 1, item 2, item 3, and item 4. And the columns are indicating the weight, right? I hope it is clear. Now, what will be inside this? What will be inside this? Inside the cells of each, say, table. Now, if you check, what is the thing we are trying to build? What is the solution we are trying to make out of it from 0, 1 knapsack? What is the thing we are trying to get at the end? We are trying to get, because it is an optimization problem, again, because dynamics solve the optimization problem. And what kind of optimization problem is this? This is a maximization problem, because we are trying to maximize something. What is that something? That something is the profit, right? So we have taken the items, we have taken the weight, we have taken the items, we have taken the weight. So what is the one thing that is remaining? Profit. And what are the exact output we are expecting? The maximum weight. That means, sorry, the maximum profit. That means this each cell will be holding some profit value, right? So now let us get back. So if there is item 0, that is there is no item at all, in that case, If we haven't seen any items at all, will there be any profit? How can there be any profit if you haven't seen any item at all? Because profit comes with items, right? If there is no item, you haven't bought anything, how will be getting benefited, right? How will be getting some profit? So that means if there is no item, we can simply put 0 over here in the first row, indicating there is no item we have checked yet. Now what is the first column indicating? This 0 simply indicating that the weight or the max capacity of the knapsack is 0. If the max capacity of the knapsack is 0, because I am saying that each cell is kind of indicating the profit value. So if the max capacity of the knapsack is 0, can there be any profit? Like, can you put anything inside the bag? Because if you put anything in the bag will be kind of broken because it cannot hold any weight. So in that case, what will be the profit? Because you cannot put any element. So in that case, the profit will be again 0. Again 0. So I hope the first row and first column concept is absolutely clear. That is, the first row is saying if there is no items, in that case there is no concept of profit. The first column is saying if the max capacity is 0, then we cannot put any item. So in that case as well, the max capacity will be, the profit will be 0, because each cell, whatever the cell is indicating, that is indicating the max profit. So it is 0, right? Now we are coming to the, what we will be solving? We will be solving row wise. Now we are going inside the row 1. If we go inside the row 1, now check what we will do. We will be taking the first item, because this row 1 is saying the first item. This is item 1. Now if you can check what is the weight of the item. The weight of the item is 1. That means if this particular knapsack, this particular bag has only one capacity, max capacity, then also we can fit this item. We can fit this item, right? What this particular column is indicating? That the maximum capacity of the knapsack is 1. This particular column is indicating that thing, right? So if the maximum capacity of the knapsack is 1 for this case, then also we can put this element, because this is having only one weight. So if we put this element, what is the maximum profit we are getting? The maximum profit value we are getting is 20. The maximum profit value we are getting is 20. So what simply this thing is saying, that whenever there is one capacity, we are considering the item 1 first, we will be going row wise, we will be going item by item. So whenever we are taking the first item and we are coming to this particular thing is indicated when the capacity of the knapsack is 1, then we can fit this, because the weight of the item is also 1. And if we fit this here, what is the maximum profit we can get? 20. I hope it is clear, right? Now if you can check, whenever we are only considering the item 1, because we haven't checked 2, 3, 4 yet, we are only considering the item 1, we are seeing the first item. Now even if the knapsack capacity is getting increased, even if the knapsack capacity becomes 2, but it doesn't really matter. You have only 1 kg in your hand, and even if you have a huge bag, but that will be only one element, because you haven't checked anything yet. So what will be the maximum profit in this case, in the whole row? It will be fixed, right? Because it will not increase, because the first item is only giving you 20 profit. Even if you are carrying a small bag that can hold 1 kg or a huge bag that can hold up to 8 kg, that doesn't really matter, because you have only one item, you have only seen one item. So you can only have the profit of 20 units, right? So in that case, even if the weight becomes 2, it doesn't really matter. 3 doesn't really matter. 4 doesn't really matter. It remains 20. It remains 20. Right? Even if the bag is of 8 kg, it will remain 20, because the profit we are getting from item 1 is 20. So how can it be increased? That's the meaning of the second row. Now we are coming to this particular one. Now if you see, what we will do, we will be checking this item. That is item 2. What is the weight of the item? The weight of the item is 3. So now, if you can check, when the knapsack, now whenever we are checking this item, we need to consider the first item as well, because we have already gone through the first item, right? Now whenever you are here, try to understand what this thing is saying. If you understand this row, I hope all the things will be cleared. Now whenever we are here, in row number 2, what is that for? That is for item 2. What is the weight of the item 2? 3. And what is the profit it is giving? 40. What is the profit it is giving? 40. First of all, just one more point I want to mention. In case of say the fractional knapsack or something like that, we need to divide, we need to make a ratio out of it, then we need to short, we need to do, and we do not need to do anything over here. We can simply start item wise, right? Now let's just get back here. Now what I am saying, for this one, try to understand, whenever you are trying to fit say the item 2, can item 2 sit here? Just try to see, because it is saying that the max capacity of the bag is 1, but the weight of the item 2 is 3. So can he sit here? The answer is no. But there is already one thing that is already sitting here. So can we remove that, or should we remove that? The answer is no. So what should be there? There should be 20. Because as I am saying, try to understand why it is 20. Because the item 1 we have already seen, and item 1 can sit when the capacity is 1. So there is no need of changing, right? Because we have already checked the item 1. We haven't checked the item 3 or 4 yet, but we have already done for item 1. So if the capacity, max capacity is 1, then item 1 can sit and item 1 is giving 20. That is the meaning of it. Now when the capacity, max capacity is 2, can item 2 sit there? No, because it is having 3. So we will be sitting, whenever we cannot check, we simply take the value from this one, from the upper cell. So it will be 20. It will be again 20. Now, if you check when the max capacity becomes 3, here comes the change, if you can see. Now, when the max capacity becomes 3, the initial value was, the top value was 20. But if you can check, now the item 2 can sit over here, because the weight of the item 2 is 3 and the capacity of this particular cell is 3. So it can sit. So if it can sit, what is the profit it is giving? 40. What is the profit it is giving? 40. So it can simply be 40, because 40 is greater than 20. So 40 will be replaced. So when you have a bag of, what is the meaning of this thing? Whenever you have a bag that can hold up to 3 kg, if it was existing that 20 was there, that is the first item was there, but if you want to add both of them, that becomes 4 kg, so we cannot fit in 3 kg bag. So we simply remove the first element and we put the second element, because it is giving more profit. Because we have a big bag, why we should put the only 1 kg if we can fit 3 kg inside it and we can get more profit? That is simply the meaning, that remove this 20 and add the second item, which will be giving you the item 40, or say profit 40. Now when it is 4, if you can check, if it is 4, then we can fit both the elements, 3 plus 1. That is, because we are checking, considering only the first 2, because we haven't checked the third and fourth yet. So if the capacity is 4, if the max weight it can carry is 4, we can fit both this one and this one. In that case, what is the total? That is profit. That is 40 plus 20, 60. So when the max capacity is 4, we can fit both item 1 and item 2, and it will be giving you the max profit as 60. I hope it is clear, right? Because we can fit both the items. Now see, even if the capacity is becoming 5 or 6 or 7 or 8, because we are only considering item 1 and item 2, and we already put both the items there and we have got the say max profit as 60, even if the weight is increasing, we cannot add any more item, because we were only checking this thing. We cannot get more profit than 60, because we have already implemented, or we have already incorporated these two. So what will be the values remaining? Even if the weight is, say, max weight is 5, then also 60. If it is 6, then also 60, 7, 60, and 8, 60. I hope it is clear that why it will be 60, because even if the bag is getting larger, you have only 2 items and you have already put it, right? Now we are coming to the third one, that is the third item. Now if you can check, what is the third item's weight? 5. So can it sit here? Because the max weight is 1. So the answer is no. So if it doesn't sit here, from where we are taking the value? This upper cell. So it will be 20. It will be 20. So where it can sit? It can sit maybe here, but not before there. So you simply copy the values from the upper cell. Now if you check, when the weight of the max capacity becomes 5, then it can sit, because the weight of the third item is 5. So if it can sit here, what is the profit we are getting? We are getting 70. So we should replace this 60. What does it indicate? If you have a bag of 5 kg where it was already existing 60 is what? 40 plus 20, that is item 2 and item 1 was already there. So remove that and only take the item 3, because item 3's weight is also 5 and it will be filling up properly and it will give you 70. That is greater than 60. So if you have a greater value, what is the problem here? Maximization problem. So we need to replace the smaller one. So that is 70. What this 70 is indicating? Again, one liner. This 70 is simply indicating we have now placed the item 3 and we have removed the item 1 and item 2 to make sure that the capacity doesn't go beyond this particular value, that is 5. Now if you can check the next one, when the weight is 6, if the weight is 6, then we can put this one and this one both, because it is 5, it is 1, 6. And if you put this 2, what is the value of profit you are getting? 70 plus 20, that is 90. 90. Now when this is 7, weight is 7, you cannot put item 3 and item 2 because it will become 8. But you can only put this item 3 and item 1. That is the max case you can do. So what is the thing you are getting? 90 again. Right? Now when it is become 8, when the max capacity is becoming 8, the last, in that case you can put this one item, you can put this one and this one and this one, because we cannot see the item 4 yet, we haven't checked it. We can only consider the first 3 because we haven't checked any value for this last 2 yet. So if you check this one, then the things might change, but for the time being we are only considering this thing, that is the item 3, item 1 and item 2. Now if you check for this one, when the value is becoming 8, when the capacity is becoming 8, we can fit 2 items, this one, item 3 and item 2, because it is 5, it is 3. So what is it is becoming? 70 plus 40, that is 110. So what is the meaning of again this cell? That is, we have removed, this one is saying that we had item 1 and item 3. Because the capacity was 7, we cannot fit item 2 and item 3. But when it becomes 8, we remove the item 1, because if we take all these 3, it becomes 5 plus 3 plus 1, that is 9. But the max it can hold is 8. So we remove the 1 and we take this one and this one. So what is the weight, or what is the profit it will give? 70 plus 40, that is 110. Now if you fill the last one, again if you see for the 4th item, the weight is 7. So up to 7, whatever the value is there, just simply copy. I hope you have understood the pattern. 20, 20, 40, 60, 70, 90. Now if you can check, when the max capacity is becoming 7, you can feed this item 4. If we feed this item 4, what is the profit we are getting? 100, and 100 is greater than 90. So we are giving it 100. So what is the meaning of 90? 90 was simply that item 3 and item 1 was there. We are removing these 2 and we are simply putting item 4 only. Because item 4 is giving maximized profit. Right? Now if we can check this one, 8. Whenever the max capacity becomes 8, we can put this item as well as this item, because that is item 4 and item 1, because it is giving 7 plus 1, 8. So what is the profit? 100 plus 20, 120. Now that's how this table is constructed. And what is giving you the maximum profit here? The last column and last row cell, this is. So that simply means that after solving this particular problem via 01 knapsack, via this table concept, it is dynamic programming. Why and how, I am telling you in a bit. But via this concept, the maximum profit you will be getting of this is 120. This is the optimized result for sure. How and why? We'll be coming back. So this is how it is getting solved. Right? Now the question is, okay, we have got that 120 is the maximum profit. But what are the items included? So you need to trace back what are the items included. Now see how to trace back. Very simple. Now what we will be doing, we are here, we will be comparing with the upper row. We will be comparing with the upper cell's value. Now if you can check, this value is 120 and the upper cell's value was 110. That simply means this value was getting changed. This value didn't remain the same. This value was getting changed. That means the 4th item has an impact of the maximized profit, because it was initially 110, but because if it was not changing, then we are taking from the upper cell, but it is changing. That means item 4 has some role to play while the profit is getting maximized. So item 4 is included. So what are the items included? Item 4 is included. Now if you include the item 4, what is the say maximum profit you have got? 120. And what is the profit of item 4? 100. So what is the remaining? 120 minus 100. That is 20. If we put item 4 inside the bag, we come via this path to solve this table and we trace back in the bottom-up manner. Just like the properties we have seen in case of dynamic programming approaches we have seen. So item 4 is included. If the item 4 is included, in that case, the maximum profit is 120 and the profit of this item 4 is 100. So what is the capacity remaining? 20. Now if you go to this row, now this row is done. Now if you go to this row, you come to the value 20 because this is the capacity remaining. You come to the value 20 and you check from the upper cell. Is this value changing? Is this value changing? The answer is no. That means what? This particular item has no impact on the maximizing profit. So that means this particular item is not included. This was included. But that means simply I am saying 0 and it is 1. Right? Now if you go to this particular cell, again 20 is remaining because that is not included. And if you check with the upper one, that is it is remaining the same again. That means the item 2 has no impact on the, say, maximizing the profit. So that is this item is also not included. Now if you can check for this and this value is getting changed. So 0 is getting changed to 20 using the item 1. So that means item 1 has some impact on, say, the maximizing profit. So that is included. So what are the two items? Item 4 and item 1. These two. If you can check, item 4 that is giving you profit 100 and weight 7. Item 1 profit 20, weight 1. So 7 plus 1 is 8 and this particular thing is giving you profit 100 plus 20, 120. So both the things are satisfied. So that's how you trace back. So that is the whole concept of how you can solve this particular 0-1 knapsack using this tabulation method. Now, there is a recursive equation. I am coming what is the meaning of this thing. But let us see, let us try to get this value, this sales value, the last sales value using this equation. Because this equation will also help you to solve this table. Now, if you want to solve this value, what is the row and column number? If you can see, C stands for sale. That is each sale. So, C of I is what? I is 4. C of 4 comma, what is W? W is nothing but the weight of that particular thing. That is the column number. This is simply the row number. This is simply the column number. So what is the W? W is 8. So if you want to calculate C of 4 comma 8, this cell, I am just trying to calculate using the formula. What is the meaning of this formula? I am coming. So C 4 comma 8 is equals to max of C, if you can say I minus 1. What is I? 4. So that is 3 comma W. What is W? 8 comma C of I minus 1, again 3, W minus Wi. What do you mean by Wi? Wi is nothing but W of 4, weight of the fourth element. So what is the weight of the fourth element? 7. So that is 3 comma W is 8 minus 7. That is nothing but 1. I am simply writing here 1 without wasting any time. 1. So plus P of I, profit of I. What is the profit of I? I is 4. That is the profit of the fourth element, this one. So that is 100. So if you can check, what will be the value? Max of, what is C 3 comma 8? C 3 comma 8 is 110, comma C 3 comma 1. What is 3 comma 1? 20 plus 100. That is 120. So nothing but you need to make the max one. So 120, 100 and 120 will be picked. So 120 will be here. So we can check using this formula, 120 is coming here as well. Right? So I hope that, like, I have talked about this formula, but what is this formula? You do not need to mug up. You do not need to mug up anything. I can promise you that thing. There is always a thing that is behind this formula. I am coming to this thing. I will also show you the tree, and I will also talk about the thing that I have just now said, that because we are applying dynamic, but there are some properties that needs to be satisfied to apply dynamic. We have applied dynamic, but now we will see whether the optimal substructure as well as repetitive subproblems, that is overlapping subproblems, concepts are there, because we have talked about in the last video that these two properties should be satisfied to apply the dynamic programming. Now let us talk about that from where this particular formula is coming, because if you wanted to understand how to solve, you have already understood that if given this one, you can solve using this tabulation method, you can trace back in the bottom up manner, right? Now we just need to see from where this formula is coming. We will be drawing a tree and we will be talking about what is the concept of optimal substructure here, how the concept of optimal substructure is coming here, as well as say the second thing, that is repetitive subproblems or overlapping subproblems, how these things are there. Okay, now let's just see that from where this particular formula is coming or what is the meaning. Suppose you have an item. Now you can either pick it or you leave it. That is, you are putting it in the final knapsack or you are not taking it at all, because there is no concept of fraction, right? So in that case, If you are picking it, what is the thing you are doing? You are kind of, removing one item because that is already picked. You will be considering the rest of the items now, and the profit of that item will be added with the maximum profit you are trying to get, as well as the knapsack capacity. That is, if the knapsack capacity initial was say C, then this item's weight, that is say W, will be removed from that thing. If you consider that item, these are the things that will happen, right? That the knapsack's capacity will be reduced and the maximum profit will be increased. So if you can check this one, because we are saying we are trying to taking the maximum value out of this one or this one. What are these two things are saying? If you are taking this, if we check this one, this is for the one, this is for the taking condition, this particular part. What it is saying, if you have picked it, then the items remains how much? That is, if initially there are I items, the items remain as I minus 1, right? And the weight of the capacity, which was initially W, that is becoming W minus Wi. That is becoming W minus Wi. I hope it is clear, right? Next is, if you are picking this item up, then what is the profit that will be added? The profit of that particular item will be added, so that is Pi, right? So that's how it is coming if you are picking this item. And if you are not picking, then this condition should be for not picking. If you are not picking at all, in that case also the item will be reduced because you have seen it and you haven't picked it. If there are 5 items, then this will be removed. So in that case 4 items are left and the weight is as it is because you haven't kind of put it, so there is no need to deduct the weight. And also the profit is there, the profit is getting added up. Here the profit is not getting added up because obviously you haven't picked it. So how the profit of that item will come? That is the meaning of this equation. So you're picking the max between these two. Either you are picking it or you are simply leaving it because there is no other way option, 1 or 0. Right? Now if you want to construct a tree of this equation, if you can see, suppose I'm just considering there are 5 items and the max capacity of the knapsack is 5 because that's what it's saying, that item number and maximum capacity. Now I am just considering for betterment or for the simplicity of this, or for say I do not want to waste much of a time here. So that's why just considering each item has weight 1 unit. There are 5 items, max capacity is 5 and each item is having 1 unit. That means you can simply think all the items will be by default included in the 0-1 knapsack. But just to show you how the tree is working, or where from the optimal substructure or say repetitive subproblems or overlapping subproblem concepts is coming, I am just showing you this thing. If C55 is there, what will happen? You can either take it or do not take it. If you do not take it, in that case, one item will be reduced, that is Ci minus 1, that is it becomes from 5 to 4 and W remains as it is. So it will remain 5. Now if you take it, then I'm just not writing the Pi again and again. I'm just simply writing the recursive equation. I'm just simply writing this part. Okay. So that is C, I minus 1, 4 and W minus Wi. What is the weight of each? Weight of each unit is 1. Weight of each element is 1. So that means 4 and 4. That is, you haven't picked this item. This is, you have picked this item. Now if you break this down again, it will be 3, 5. Same thing will be happening again and again and again. It will be 3, 4. Then again it is not picked, so that is 4, that is it becomes 3 and it remains 4. Here 3, 3 and so on. Right? Now I am just wanted to show you from where that optimal substructure concept come, because each time you are going in the smaller subproblems. So that's why from 5 it is becoming 4, 3, 2 and so on. So we are coming down. So you are solving the smaller problems and you are trying to find the maximum profit out of it, and you are then trying to merge them back. This is the concept of optimal substructure. And from where does repetitive subproblem or overlapping subproblem come? If you can check, there are repetitions, C34, C34, C24, C24, then C23, C23, like that, C24 again, C23 again. So there are so much of repetition if you can check. So the initially, if we do in brute force manner, it was order of 2 to the power n. But if we simply do this using the dynamic programming, whatever we have done just now using the table matter, then it will be simply, if it was I and W, say there are X element and there are Y is the maximum capacity, then it will be simply, or say there are X items and then Y is the maximum capacity, or say there are N number of items and W is the capacity, then this is the complexity. Because if you can say this is the size of the table, N cross W, or say N plus 1 cross W cross 1. Whatever. It was initially 2 to the power n plus 1 or 2 to the power n, anything like that. But here it is becoming order of n cross W. So that is all about the things, how the optimal substructure is coming, how say the overlapping subproblem is coming, how to solve, why it cannot be solved using greedy. So I think all the things that were there in 01 knapsack, I have talked about every point in detail. So I think that you have understood all the things and everything made sense, and I hope you do not have any doubt regarding the 01 knapsack. If you have, please comment down. So thank you for watching the video and stay tuned for the next videos.